better. I like when people say great. Oh, awesome. Yeah, the test was cut by those points. Yes, so test 6 grades are out, posted, and test 6 is out of 75 points. So if you check your rainbow grades, you should see exactly that. I know it's if you just go on Submiti, it's going to show you that it was worth 100 points. Well, it is not true. It is out of 75. All right, good homework 6 and test 6 grades went well. I think so. Yeah. You know what their average was on test 6? Can anyone guess? Out of 75 points. Yeah, it was 75.5, so it's like 97%. So I'm thinking about introducing a reverse curve. So why don't we have a sub-mini poll so that students vote on curving this exam backwards? Yeah, reverse curve. You can call it Kuzmin curve. I'm just kidding. I don't think anyone would do a reverse curve. All right. No need for the submini poll on this one. All right. Yeah, and so why don't we get started? Oh, sorry. If you thought even for a moment that it could possibly be true, I really sorry. It was meant to be a joke that that I was hoping everyone would understand from the very beginning that it was a joke. And I'm starting sharing my screen, and just need to organize my windows as usual. We'll try to do it real quick. No, this is not our last lecture. This is our last week, but we are going to have a lecture on Friday. And I sincerely hope that people come and show up. So it's going to be the material that obviously is not going to be on any test or homework or anything, but we still are going to have the lecture. And it's going to be a very general, very high level, very soft introduction to parallel programming. So, only the real ones are showing up. Yeah, I like it. Any predictions to how many students will show up for the last lecture? I'm hoping for the best. Really, I'm optimistic. I think this class is doing really good, and I hope that people would still show up. Just to relax and attend the last lecture. All right, and. So yeah, one thing I wanted to show you is this. This is just completely mind blowing, right? So as of right now, we have 3 students who are above their perfect, and perfect. The way Rainbow Grades compute perfect is 91 because we still haven't graded the last homework and the last test. So Rainbow Grades consider that to be like your lowest grade for everyone, right? Which it drops. So that's why the perfect grade, right, as of right now, is just missing their the project, 9 points for the project. Okay, so those are real points. So you're looking at these people, right? So 2 of them are above A at this time. So even if these 2 people skip homework 7 altogether, skip test 7 altogether, and get a 0 on their projects, they still gonna get an A in this class because those are real points, right? So that's something that doesn't happen that often. So yeah, and one person got really close to 93 to this A threshold, and the actual thresholds are going to be slightly lower than what is in their syllabus, because remember we had two tests where we curved them slightly by lowering the curves on those 2 tests. So those curves would be incorporated in the overall thresholds for their letter grades. So that third person here might be actually within the A as of right now as well. And yeah, I don't know if they're in the lecture or not, but hopefully they are. And I had to. You see, I redacted the slide. I cannot disclose the names of people unless they are okay with that. But I also posted some interesting stats. If you got tired of preparing for all their exams and doing all the coding for the project and the homework, and you wanted to take a moment to relax a little bit and look at the stats. So I posted stats on the Submiti forum. So there are quite there are several a good number of nominations, and they so for the update to Rainbow Grades, which I did just this morning. So I will update, of course, their nominations when we get everything graded. But as of as of the weekend, you could see that there is a number of students, different students, who got nominated. For different things, like the best person to do on the homework is not actually, someone from their top 3 overall in this class. Okay, so I think we had like 14 different people mentioned in different nominations. So you can take a look and see if you recognize your name under one of those student 1, student 2, student 14, and what so forth, and so forth. Yes, grade cutoffs are going to end up a little bit earlier, a little bit lower because of their curves on. I believe that there were 2 tests when we very slightly curved them. Okay, it's someone is asking me about their decision to skip the homework. It's up to you. I can only recommend that you still do it, but I understand if you don't. I understand that everyone is very tired, overloaded, stressed out. Not only by this class but by other classes as well. So I won't hold it against you if you decide to skip. That would be my answer. Yeah, same for showing up to the exam. I think it's still worth it, but it's largely up to you. If you decide to skip the exam or the homework or both, just make absolutely sure that you do your math correctly, and double check everything that Rainbow Grades tell you now to make sure that you do not end up skipping the exam and then regretting, oh, I'm just I just wish I came to the exam and got 10% of the credit, because that's what I need to get to my desired grade. Okay. If you skip the exam and the homework and the project, then the grade is going to be what is currently on Submiti. Yes. So the number of points that you see, like I was showing, it was 93 and 94 something to the top 2 students in the class. Then yes, those are real points. If you skip project, homework, and the last test altogether, that's what you're going to get. It's of course just going to be not out of 91 as it is now, but out of 100. Okay. All right. And let me check to make sure that our panelists are here. Okay. Well, I see 2 of them. If we have other panelists, please be active. Please identify yourselves and make sure that you answer some questions. All right, so grades are posted for everything all the gradables that have been submitted. All right, so again, our TAs this semester are just awesome, and the mentors, of course. And they are done grading Test 6, Homework 6, Lab 7. So the only 3 things that are left are Homework 7, Test 7, and the project. And all of them are due in the future. So Homework 7 is due tonight, and Test 7 is tomorrow, and project is due the last day of the classes. Okay, and yeah, we're gonna have panelists on Friday. So because maybe some people still need a few maybe they need that quarter of a point to get to their next highest grade modifier. So who knows? Yeah. So we're gonna do it. We're gonna run everything on Friday as we normally do. Okay. So for the exam tomorrow, one thing I wanted to mention is that it is one of those days, one of those Wednesdays, when we have some math exam following our compwork exam, immediately following our compwork exam in the same room. And we were asked to make sure that we are out of the room by 7:55 p.m. so that the math people can start their exam on time at 8 o'clock. Okay, so we have 110 minutes. So we try to start at 6 and finish at 7:50, and then 5 minutes to collect the remaining exams. So please, if you can, try to arrive to the testing location early, at least 10 minutes early, to make sure that we have minimal disruptions and that we start exactly on time at 6 o'clock sharp. And I understand some people, have labs, and they would not be there at 5:50. But everyone who can, please try to come to your test tomorrow earlier. Okay. Yes. So Samyuth and Ethan are going to give a presentation on their Minecraft thing, and yeah. So you will just go in the very beginning of the lecture. Okay. So we'll start with your demo presentation, however you want to structure it, and then we'll continue with our chapter 5 thing. Does that sound good? Okay, cool. No, not right now, on Friday. Okay, so that's probably it about all the grading and logistics stuff. So let's continue with our chapter 5, right? And see how far we get. So hopefully we go through, well, we definitely should go through all their cache, through the remainder of the cache topic, and then hopefully, cover the bulk of their virtual memory topic. All right. And I believe that's where we left off. So and let me just remind you the context of our discussion. So we were talking about all the direct mapped caches, and we were doing some calculations for the policies, and part of those calculations was actually the cost of a miss, right? So just to remind you, a miss is when we have an access to an address in memory, and it turns out that that memory address, the value from that memory address is not in the cache. So our cache has to reach out to the data, to the main memory, and actually get that value. And main memory is very slow. Remember, DRAM is so much slower than SRAM, so that this penalty becomes very significant. So it takes several orders of magnitude more time to fetch value from SRAM than it is to read value from SRAM from the cache memory, right? So and you can see from that example that we reviewed last time. So it's roughly 1 to 100, so 2 orders of magnitude. So what can we do about it? And what additional examples can we look at discussing this very, very slow main memory? So here is a specific example of a main memory that supports cache. So it is just an example, but it is pretty realistic. So our typical main memory DRAM would have a fixed width, which is 1 word. Okay, so it's not the only option, but if you recall all our previous examples with memory, we were always saying that, well, our memory reads 1 word at a time, which means that its width is one word. So you supply an address, and the memory spits out one word at you. Okay, and that's why it's called, memory with a width of one word. And of course, then it is connected to the CPU, and of course, all the parts of the system are synchronized together by a common clock. So there is this. That's why it says connected by fixed width clocked bus, and bus clock is typically slower than the CPU clock, and that is, basically the reason for that is that it doesn't make sense to make this bus run any faster, because that would not be supported by DRAM, because DRAM is slow. And to give you a specific example, let's assume that it is taking one bus cycle. Again, bus cycle is not the same as CPU clock cycle, but it still gives us some reference point for computations, right? So one bus cycle is to transfer the address that we want to read from our main memory, right? Because we need to send the address from the CPU to the main memory, to our DRAM. Then it takes 15 bus cycles to actually read the memory or write the memory. So to perform our DRAM access operation, and then one bus cycle to send the value back. All right, the value that was read from DRAM needs to be delivered from the output, from the data output of DRAM to the CPU. Right, so it's going to be one. Why 15 specifically? It is just for a specific microchip, for a specific DRAM. So it is just from technical specifications, right? From the data sheet for a particular memory. Okay, and it doesn't matter that much which one it is, but the ratio, like how long it takes to transfer address and transfer data, relative to how long it takes to actually for DRAM to read their value from its own internals, is pretty typical, right? So it's like you see it's a factor of 15. Okay, so what if we need to read a forward block? So we are circling back to our cache, and we are assuming for this example that our cache block size is 4 words. Okay, but our DRAM is still 1 word wide. So that means that when you have a miss, you have to bring in the entire block into your cache from your main memory, and that block is 4 words. So that means that you have to send address once. Okay, so this is that one bus cycle from here, and then you have to read 4 words, right? Because of this is this 4, and each word takes 15 cycles to read. That's this 15. And then you have to transfer the data, your 4 words, back to the CPU, right? So again, it's 4 words because it's a 4-word block, and it's 1 clock cycle because it is 1 bus cycle per data transfer. So you sum it up, you end up with 65 bus cycles. Okay, so and then if you think about the bandwidth, then how many bytes did we transfer? We transferred 4 words. Each word is 4 bytes, so it's 16 bytes, right? Because it's 4 by 4, 4 words, and 4 bytes per word, right? So it's 4 by 4 in 65 cycles. So we compute the average bandwidth as just 0.25 bytes per cycle. And you can see why this is such a low number, because the bulk of the time out of those 65 bus cycles, 60 cycles, we were actually not transferring anything over the bus. We were just waiting for the DRAM to read those 4 words of data from itself, from the memory. Okay, and that's why obviously this is, in this example, we see that our bus is not utilized very efficiently. Okay, so what can we do? Can we do a little better? So the organization that we have been reviewing so far in the previous example is this one. It's one word wide memory organization. So you see, here's our processor, and it is connected by the data bus with a cache, and then cache is connected with a data bus with memory. Remember, we can only go from level to level, right? The processor cannot jump to the memory. There's no transfer possible if we exclude the cache, right? So the processor doesn't talk to the main memory directly. All right, and the memory is so slow that we have to wait until it has the data ready, and that's why we were getting just this quarter of a byte per cycle bus bandwidth. So what can we do better? Well, one thing, we can go with a wider memory organization. So we increase the number of bits in our bus as well. So if we need to read 4 words at a time, we can make so the width, if we show it like that, right here, it's just 1 word. So we can actually go with a wider bus, which would be 4 words. And then our miss penalty becomes much smaller because we would still have 1 bus cycle to transfer data, but because our bus is wider, we can transfer all 4 words at a time. So we only pay this 15 bus cycles penalty once, okay? Because we transfer the entire 4 words at a time. And of course, our memory has to be designed differently so that it supports reading 4 words at a time instead of 4 times 1 word at a time. But it is actually not that hard to do. Okay, so if we organize our system, our memory system like that, we would have 17 bicycles of the miss penalty, and that translates to a much better bandwidth or bus utilization, right? So it's almost 1 byte per cycle, which is not that terribly bad, compared especially to the previous example. And it turns out that we can do even better. That if we have memory organized as several banks, and we call this interleaved memory organization. You see how we have 4 banks here? Then those banks can kind of work in parallel, fetching the data, reading or writing, in any case, accessing the data in parallel. And in this case, we don't even have to go with a wider bus. So you see the bus itself is 1 word here, but due to memory organization, due to having those banks, we can do much better than in our 1 word wide memory organization. So you have to transfer the address. You have to wait 15 cycles, bus cycles, for these 4 words to be accessed by these 4 memory banks. Because they work in parallel, we only pay this 15 bus cycle penalty once, and then we have to transfer the data in 4 bus cycles because our bus is only 1 word wide. Okay, so as you can see, it sums up to 20 cycles, 20 bus cycles, and gives us the bandwidth, which is not as good as our 4 word wide memory organization, but it is still leaps and bounds better than what we started with. Remember here it was 0.25 bytes per cycle, right? So 0.8 is of course several times better than 0.25. And of course this organization is much cheaper because you don't need to have a bus which is 4 times for 16 bytes wide, right? You can only have the bus which is 4 bytes, 1 word wide, and of course it is much cheaper. Would you need more circuits if you process 4 words at once instead of? Yes. So I think I just I answered this before I even read your question. So yes, you would need more circuits, definitely, and more wires. So that is of course costly. All right, so this is just an illustration why we care so much about misses, and why misses are so expensive. And while there are some ways of, we can play with memory organization as shown here, it is still not so good, right? You still have, at least 15 times longer here that you have to wait for the memory to access the data. Not to mention that this bus cycle is not the same as the CPU cycle, right? So the bus that will be the frequency that this bus will be running at is typically going to be uh, slower than the frequency that their CPU runs on, that the frequency of the bus inside the CPU. All right, and in the forward wide memory, why don't you multiply by 4 anywhere? Well, because we read all forwards, right? So here, this is giving us 4 words at a time, right? So if it takes 15 bus cycles to read the value from the memory, we only pay this penalty once because we read 4 words at once. We don't read 4 times 1 word at a time. We read once. We supply one address to our memory. So if you imagine, this is our memory. We supply address, which is 32 bits, and it reads 4 consecutive words. So it produces the data, which is 128 bytes, right? So it is 4 times 32, if I did my math correctly. I hope I did. Okay, is that making sense? So and of course, the key point in designing our cache systems and our memory hierarchies in general is how do we measure cache performance? So if we have several options for how to design a memory hierarchy, and we will shortly see that we have a lot of options, maybe too many options, then of course we need a way to compare them and guide our decisions. Like, do we go with this option or with this option? What is going to yield best performance? And of course, that's not a trivial question because it will depend on many variables, and that's why we need to have a way of assessing cache performance. So here are the components that we need to consider. So first, program execution cycles, right? So this is basically the number of CPU cycles that your program takes to execute. And it includes cache hit time because, of course, if you're performing any LW, SW load store operations, then they they might still take time, right? They might or might not complete within one CPU clock cycle. It depends. And then, of course, their memory stall cycles, right? Mainly from cache misses. That's the biggest. That's going to be the biggest component. Okay. We know that hits are relatively cheap, right? Because when we have a hit, we only read from this very fast SRAM, which might be as fast as CPU in relative terms. But when we have a miss, we have to rely on cache, bringing the value that we need from main memory, and that means tens, if not hundreds, of cycles, and that is very slow. Of course, what is going to happen to our processor while it waits for the cache to satisfy this memory access operation? It's going to stall, right? It cannot continue because it cannot just save their, just put aside this memory access load or store operation and then come back to it later. So we have to stall them. We have to stall the pipeline. And of course, this is very costly. So this thing is the major component of their overall overall memory-related latencies. And therefore, we are primarily concerned about memory stall cycles. So, we shouldn't discount this at all. We shall see that, yeah, we will come back to considering this hit time as well. But this component, the latency, the amount of time wasted because of the cache miss is going to dominate the overall latency, of course. And so memory stall cycles, how do we compute them? Well, we need to know how often they happen, miss rate. We need to know what is the cost of each miss penalty, and then we need to know how memory intensive our program is. So this third component here, memory accesses per program, uh, characterizes how often your program accesses memory, performs LW or store W. Okay, so it's a pretty, I think, intuitive formula, and then you can rearrange it a little bit so that you express the instructions per program, so total instructions per program, and then compute the misses per instruction. Okay, and then if you think about it, right, if we, if we want to go back, we see, well, instructions cancel out, and then it just misses per program. So really, let me use a different color. This quantity here is exactly misses per the entire program. Okay, so it's just the same formula written slightly differently depending on which initial data you're given. You might be able to just plug it in without converting one quantity to the other. All right, and here is an example that demonstrates how we use this formula. So we are given separate instruction data memories, and we have iCache miss rate of 2% and Dcache miss rate of 4%, and it is quite realistic. So typically we have data cache missing more often, just because iCache instruction cache we never write to, and typically instruction memory is smaller than their data memory. So no matter how you slice it, it's quite typical that iCache miss rate is going to be lower than the Dcache miss rate. And here we have specific percentages, specific values. So miss penalty is 100 cycles. Again, this is pretty typical. Base CPI is 2, so this is the fastest that our processor can go. Assuming ideal cache when there are no misses. Of course, it's this ideal perfect case is never going to happen in real life for any sufficiently long programs, but this is our base CPI, and we are going to need it for our computations. And then we know the percentage of memory access operations in our program. So we know that load and stores are 36% of all instructions. So roughly every third instruction in our program is either a load and store. We need to know that because that determines how likely we are going to hit uh, a miss. How likely we are going to encounter a miss. Imagine out of 100 instructions, you only have one load instruction. Of course, the probability that this one single instruction is going to cause you a miss is much lower than if you imagine that 90% of 90 out of 100 instructions in your program are load and store. Okay, so of course, then the probability of encountering a miss is going to be much higher. It's like if you only drive once a year for 10 miles, your probability of getting into an accident is going to be much lower than your probability of getting into a car accident if you drive every day 200 miles. Okay, and of course, insurance companies know that. So, I can only envy your insurance if you drive less than 1,000 miles a year or something like that. All right, so now from what is given, we are trying to compute the performance of our cache. So we need to compute the number of miss cycles per instruction. So we know that 2% of memory bound or memory access instructions in result in this 100 cycles miss penalty. So for this translates into other into 2 miss cycles per instruction on average. All right. So basically, it means that in your entire program, if it is 100 instructions long, then the additional penalty per instruction due to cache misses is going to be 2 clock cycles. Okay, and if you think about it, it's huge. It's a lot. So for Dcache, it is they're a very similar formula. So their percentage of our miss rate, 4% times 100. So this is our miss penalty. Okay, so this is 100 from here. This is 100 from here. This is 2% from goes here. 4% goes here. Okay, and then we have to discount it by 0.36. Okay, this is this 36%. It goes here. Why don't we have this additional term in the iCache miss cycles computation? Well, because when you fetch data from instruction memory, then every instruction is going to be a read from the instruction memory. So you can imagine there is this like 1.00 factor here, right? Because every instruction that you execute needs to be read from the instruction memory. And for Dcache, for data cache, of course, only instructions that do load and store have a potential of, giving you this miss penalty. That's why we discount by this 36%, right? So this is going to be 144, and that is 144 miss cycles per instruction due to Dcache misses. And now the actual CPI we are computing as our base ideal CPI in the absence of any memory misses, cache memory misses. So that's this two, plus the extra penalty from iCache misses, which is this, plus extra penalty from Dcache misses, which is this. Okay, and it all gets to 544. And now if we think about it, now we can contrast their values. So our processor is capable of moving forward at the rate of 2 clocks per instruction. Okay, but in fact, the actual CPI that we will see per instruction is 544, almost 3 times slower. Or if we compute exactly 2.72 times slower, that our program will execute compared to an ideal case when we do not have any misses and any miss penalties associated with those misses. Okay, so you see that the cost of the cost of going with many misses is significant. And if you think about it, we don't have that many misses, 2% for I memory, 4% for D memory. So those are relatively low, you might think, but the penalty for each miss is so huge that you can see it translates to a significant slowdown of the overall execution of the program, right? So this actual CPI, of course, is the average CPI, and you see, how much slower it is compared to their ideal CPI. So we definitely want to minimize the number of misses. That's their story behind this. All right, and here is a slight modification of the previous example, which I am asking you to do as a poll. This is a mini poll, as our pop quiz. All right, and in the meantime, we are moving forward. So clock rate, cache performance. If we think about it, and if we play with numbers, right, you would arrive at this as one of the examples of what you could do. If we double the clock rate of the processor, okay, we are not changing the cache miss rate, and we are not changing the miss penalty. So the cache will not improve, so the speed up is not going to double. Okay, so this is just to help you a little bit with with the previous with our pop quiz. Okay, just some thoughts. Okay, so far we have been concentrating on our miss rate and associated miss penalty. However, hit time is also important for performance, not nearly as much as the miss rate, miss penalty, but nonetheless. So if we want to incorporate the hit time in our considerations, we have to come up with another metric that we can use to assess the overall penalty associated with memory access instructions. And we call this average memory access time, or AMAT. So AMAT is a hit time plus miss rate times miss penalty, okay, which you can think of a miss time, right? Miss rate, how often misses happen. Miss penalty, how costly each miss is. So AMAT is a total hit time plus miss time. So here is a quick example of computing AMAT for you. So if we have a CPU with a 1 nanosecond clock and the hit time is just 1 cycle, so essentially we pay no additional penalty. But miss penalty is 20 cycles, and iCache miss rate is 5%. So the AMAT would be 2 nanoseconds. How we get this? So just from the formula above, our hit time is 1 cycle, and then we have miss rate. So 1 cycle obviously is 1 nanosecond, right? So it is. So if you do the dimension analysis, right? So this one is actually 1 nanosecond, right? It's not 1 cycle. It's really 1 nanosecond, right? But the hit time is 1 nanosecond, right? Because it's 1 cycle, and we know that the clock has the period of 1 nanoseconds. And then 5% is our iCache miss rate, and 20 cycles here, right? So this is 20 cycles. And again, it is going to be one cycle, but we know that 1 cycle is also 1 nanosecond. So there is this implicit conversion from cycles to nanoseconds, but make sure that you realize that AMAT is, as it says, it's whatever, but it's time, right? So it's average memory access, but it's time. So it has to be in some units of time. Okay, so if you get this question somewhere on the exam or whatever, right, do not say AMAT is 2 cycles, right? If you know what the cycle is, then multiplied by the period of the clock, and then express it as some number of nanoseconds, microseconds, whatever your unit of time is. Right. So you see 2 nanoseconds is AMAT, so basically it's 2 cycles per instruction. So you see versus potentially ideal case where our instructions proceed at 1 instruction per clock cycle, or 1 cycle per instruction, we are actually slowing down by a factor of 2, just because again of the effect of their misses. But even in the absence of misses, this AMAT would still be 1. Even if we eliminate the misses, we still have the hit time, right? So the hit time is still 1 clock cycle. Yes, the slide that I showed is not in their slides that you have, because I think it's considered to be an answer. Okay, so I guess when I was preparing the PDF slides, I disabled that slide, and then somehow in my PowerPoint it's still enabled. So it's too late to do anything about it. So take this hint, but yes, it's not in the slides because it is considered to be a solution to the pop quiz. Is that making sense? All right. So the summary. When our CPU performance increased, then penalty becomes more significant, right? because your penalty becomes a more significant portion of the overall formula, right? So it's like if my entire trip is 10 minutes and I have to spend 5 minutes at the gas station, then I wasted half of my time, you know, doing essentially something that does not get me closer to my destination. But if my entire trip is 6 minutes and I spent 5 minutes, fueling my car, then it's even a bigger percentage of my trip that I just spent doing something that is not directly related to getting to my destination, right? So if we decrease our base CPI, then a greater proportion of the time is going to be spent on memory stalls due to misses. And if we increase the clock rate, then memory stalls account for more and more CPU cycles. So that means that we cannot neglect the behavior of the cache, and especially the effect of the misses when we evaluate system performance. So what do we do with, how can we decrease our misses? Any thoughts from anyone who hasn't read the textbook yet, or hasn't read beyond this, but has an idea of what we can do to decrease our miss rate? Well, if you think about it, what was the root cause of misses? It was the fact that we were trying to find the value from some memory address in our cache and it wasn't there. Why wasn't it there? There might be several causes. One, this memory access, this address has never been encountered before. That's why it's not in the cache. And there is a way to kind of battle that cause of misses. But there's also another possibility that the address that we are trying to access right now was accessed earlier, but then it was replaced because there was another address access that mapped to the same cache line or block of cache. Okay, so it was there, but it was replaced. And why was it replaced? Well, because as we remember, in a direct mapped cache, there is always one block that corresponds to multiple main memory locations. So those memory locations, they compete for that single block, right? 4 to 1, four main memory locations compete for a single block of cache. And of course, it can be not necessarily 4, it can be 2 or 8, or typically it's a significant number. And that competition causes the replacements. And if we could somehow ease this competition and say, well, maybe with our cache, if there is no room in that particular block, but there are empty, unused blocks somewhere else in the cache, we could use those blocks to bring our new value in, right? So instead of this rigid formula where there is a direct correspondence between the main memory address and the cache block, and that's why this is called direct mapped. Okay, maybe we can, uh, relax the restrictions a little bit and allow the memory address to map to potentially several entries or lines in our cache. And this is exactly the idea behind associative caches. So with associative caches, there is, it is somewhat conceptually similar to a hash table. Yep. So uh, with associative caches, we can vary their degree of associativity. Okay, so it's getting more interesting than with a direct net cache. So when we say that any given memory address can map to not just one block of cache, but to a number of block caches, of course the question is, well, what is the size of that set of entries in the cache to which this memory address can be mapped. And that answer can vary. So we can have n-way set associative caches where we have a number of sets and each set contains n entries. Please, 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 it's a very common mistake. Somehow, if people tend to think, or sometimes, make a lot of people who are new to associative caches make this mistake with the terminology. When we say n-way set associative, n doesn't mean the number of sets, right? So we have set and there is a certain number of sets. So n is not the number of sets. N is the number of entries, cache lines in each set. And all sets will have the same size, right? So this n is going to be the same for all sets, but n is the size of a set, not the number of sets in the cache. So please make sure you make a mental note on this. It's just a notational thing, right? So, but when we say two-way set associative, it's not two sets, all right? It's two entries per set, and the number of sets, typically would not be actually two. All right, so that's the n-way set associative cache, and in this case, we have a block that that is part of a set. So a set contains multiple blocks, and block number determines which set this particular address, this particular block is going to go into. So our formula for determining the block number becomes block number modulo sets in the cache. Previously, instead of sets, we were doing modulo the size of the cache, where the size was the number of entries. Now we're not doing the size or the total number of entries in the cache, we're doing the number of sets. Note that this is number of sets. That's this quantity, right? It's not the it's not n, it's not the number of entries, it's the number of sets. And of course, if you know the total size of cache, so if you, for instance, know that you have 128 entries in your cache, and your cache is two-way set associative, then how many sets are you going to have? Anyone? 64, exactly. Yeah, we have two entries per set, so we're going to have 64 sets. All right, and then, of course, the problem becomes like, how do we find if their memory address that we are trying to access, if its value is in the cache or not? Previously, we only had one location to check. Now we have to check all entries in a set, because that value from that memory address could have gone into any of the entries within that set pointed to by this formula, right? And so that means that we have to use to search all entries, and that is pretty can be pretty expensive, and we can do with so with n-way set associative, right? Obviously, we only need n comparators, right? Because we only have n entries, which is less expensive than our other option if we do a fully associative cache. Fully associative cache means there is just one set, and that means that any memory address can go into any block of cache because there's only one set. Okay, so we allow a given block to go into any cache entry. And that, of course, requires that all entries are searched at once. That requires as many comparators as there are entries, and that can be very, very expensive, right? Because it means a lot of additional hardware. It means a lot of, we need a lot of real estate on our, cheap servers to dedicate to this. All right, and here is another pop quiz for you. All right, poll number 2. Hopefully I didn't mess up the order, so please check to make sure that the second quiz is exactly what is shown in in my slide right now. But we are moving forward, and here are associative cache examples. So we contrast direct mapped with fully associative with set associative. So with direct map, we have we are searching for the address, and we find the index in the cache where the value from the address might be. That's the only location, right? Block number 4. If the value that we are trying to access from data memory or instruction memory, whatever, from our main memory, if it's in the cache, it will be in that block at index 4. And then you remember what happens with direct map caches. We have to check the valid bit, and if it is 1, we have to check our tag, and if the tag in cache matches the tag which is part of their memory address that is coming from the instruction, then we know that yes, it's a hit. This is it. We found the value. It is in the cache. And if not, it's not in the cache. There is nothing else we can do. No further action is required. All right, with a fully associative, the value that we are searching, they could be right. So this cache is just one big set. So the value that we are searching for, it can be in any of their lines of cache, and we have to. You see those arrows? They show that we have to check all entries and see if the tag matches or not. And if it's a matching tag, we found the value. It is in the cache. If none of the searches is successful, it means that we have a miss. But we can only deduce it's a miss after we searched through the entire cache and examined every single tag. So this is fully associative. And this is set associative. So can someone tell me how many way is this set associative cache? How many? So when we say n way set associative, what is n in this case? Exactly, it's two-way set associative, right? Two-way. Why? Because we see this is the set number. All right, so this is set number 1, this is set number 2, this is set number 3, this is set number 4. So we have 4 sets, but each set has 2 elements, so it's two-way set associative, and it matches what is shown here, right? From the memory address, we determine the set, much like we were determining the index with the direct map cache, but now it's not just the index, it's the set number. And that set may contain multiple entries, in this case 2. So we have to search for whether the value is in the cache or not, but only within the set. And that's why there are 2 arrows here. So we only search this first set, because we know if that value from that memory address is in the cache, it has to be in this set number 0. Okay, so we only have to search that set. All right, and here is the entire spectrum of associativity. So imagine you have the same size of cache in this little example with 8 entries, and you are deciding how to organize your cache, whether to go with a direct mapped or two-way set associative, or like what are your options. Well, one extreme is a direct mapped cache, so we also can call it one-way set associative. Why? Because you can think of this cache organization as having 8 sets where each set is exactly 1 entry. Okay, so that's one extreme. The other extreme is fully associative, and since we only have 8 entries in this example, we would say it's 8-way set associative. But it's only for this case, right? If you have more entries, then of course this would be 16-way set associative and so forth. So that's why we typically say just fully associative to indicate that we have one set, but that set contains all entries, all 8 entries in our case. And of course, then there are other ways to organize. So we can have a two-way set associative. So we have 4 sets. See, 4 sets, and each set is 2 entries. Of course, each entry is a combination of tag and data here, tag and data here, right? So here are your two entries, but it's the same set. Okay, and that's why it's two-way set associative. And of course, we can have four-way set associative where we have two sets, but each set has four entries. All right, and here is an example on associativity. And we are performing the same access operations where we access memory at addresses 08068. What is going to vary is the organization of the cache. We will try direct mapped, two-way set associative, and fully associative. And what are we trying to observe here? We're trying to observe the miss rate, because we were hoping that going with set associative caches is going to reduce the number of misses, because we would have more freedom in where an element that we are trying to bring into the cache goes, from a very rigid, direct mapping for a direct map cache to a fully relaxed, kind of hippie style, fully associative cache where you can just go anywhere you want, right? In this cache, anything can go anywhere. All right. So and that's what we are trying to observe here, and we can do the simulation. And I have the right 08068. So I'm just going to copy this so that I don't forget. And we need to also configure our cache. So I'm going to use this simulation. All right. So let's check. Right back, right on allocate, and then cache size 4, because it is here. All right. So obviously it has to be the power of 2. So memory size is 32, just to make things easier. Right. So it's not the number of address bits in the memory. So it's the memory size. And then offset bits is 1. So one note that I need to make here is that this simulator assumes that memory is word addressed, not byte addressed. That's why offset bits that I'm entering here is not 2, as would be in almost all our other examples, but it would be 0, because this simulator, this online simulator, does not allow us to access individual bytes within the word. So it assumes that the memory is word addressed, not byte addressed. All right, and then our first instruction would be accessing 0 address, and then 80068. Oh, come on, 08068. All right. Did I get it right? 08068. Yeah, I think I got it. All right. So we need to submit. So we configured our cache. So see how it updated, and so we have our cache size 4, and we are ready to start. So we submit our first instruction, load from address 0, and you see that the instruction has been converted from hex to binary. This is the instruction breakdown right here. And then next is we dissect the address, and then we figure out the index of the cache, right? So it's going to be 0, 0. And right, so this part you ignore it, right? Because this offset is 0 bits, so it's not even part of what we are considering here. And we have 2 zeros here because our cache has size 4, so we need 2 bits for the index. And then the tag is going to be the remainder, so it's going to be these 3 bytes, these 3 bits. So in total, we have in our memory address, we have 5 bits, 2 and 3, 5. Why 5? Because our memory is just 32 bits, 32 words, right? So the size of our memory is 32. So to address those 32 words in memory, we just need 5 bits. That's why, here we have 2 and 3, 5. All right. And I'm just moving my windows a little. And valid bit is 0, obviously, when we just started. So when we power on our system, valid bit is set to 0 for the entire cache. So obviously it's a miss, and therefore cache needs to be updated. So we need to read the value from main memory and bring it into the cache, which we do. So now you see valid bit is 1, tag is 0, and we have this word from address 0 stored in our cache. All right, so that completes this first instruction, load 0. Next instruction, load 8. We submit the instruction, and we look at it, and it turns out that it maps to the same block of cache. It's a direct map cache, remember, and so it's the same 0, 0 for the index. Tag bit is different, but we will see what is going to happen. So valid bit is 1, so that's a good thing. Last thing to check, do we have a match? Tag from the instruction is 010, tag from the cache is 000. Uh-oh, we don't have a match, right? So regardless of the fact that the valid bit is 1, tags do not match, which means yes, we have a value stored in the cache. It's a value from some memory address that maps to index 0 of our cache, but it's not the word that we want. We want word from address 8, and we have cached the word from address 0. That was our previous instruction. And therefore, we have a miss. What happens? Well, it means that we need to replace. So we bring in this word from address 8, see block 8, and now it's in the cache. And we are done with the second instruction. Well, you see that so far we are not doing that great. We have a miss rate of 100%, right? Because out of 2 instructions, both were misses. So our third instruction is load 0, load from address 0 again. We submit it. You can predict what is going to happen, right? Of course, it maps to that same block of cache, and we have a valid bit of 1, but we have block 8, not block 0 stored there, or we have data from memory address 8, not memory address 0 stored there. So we're going to have a miss, unfortunately, and so that means we have 3 misses for 3 instructions. All right, so our miss rate is 100% still. But now we have block 0 here in this line of cache at index 0. Next is load 6 instruction, load from address 6. We break it down and we see, oh, finally, it's not going to map to our poor index 0. It's going to map to index 2. So we can finally avoid torturing that same block. Of course, we're going to have a miss right now, right? Because that block has not been used before, and we bring in block 6. So currently in our cache, we have word from memory address 0 and word from memory address 6 cached, and we have 100% miss rate. So we have just one instruction left, load from address 8, and you see that, oh, it maps to that same index 00, and we can predict, hopefully you can predict that we are going to have another miss, right? Because we need address 8 and we have cached data from address 0. So it's going to be just that, and we are done. And we executed 5 instructions. We never had a single hit. right? Not so good. So what about let's obviously try a different degree of associativity. So let's try two-way set associative, and I'm going to open it in a new tab. So we need to configure our cache. So cache size 4 and 32, that stays, and offset bits is 0. And there is the replacement policy here that we can specify, right? Because now we have a choice of which, if our set is full, now we have several options for which element currently in the cache to kick out of the cache, to replace. And here are, three of the policies that there are others, but LRU and random are the most common ones. Random means we replace the element at random. LRU, least recently used. It means that we replace the element that hasn't been used for the longest time. Okay, so for our example, it really doesn't matter that much, because we're trying to just demonstrate the number of misses without regard to replacements. All right, and we are going to configure our cache, and then first would be 0, and then we're going to have those same instructions, and let's just go through them. All right, so the first one is going to be a miss, right? Because we are starting with a brand new cache, all right? Crash. Okay. And see how their cache structure is now different, because it shows that we have not just 4 entries, but we have 2 sets of 2 entries each. Okay. And so when we attempt to load from address 8, we have a miss again. And then we are deciding where do we put our data that we read from address 8. Where do we put in the cache? Do we replace the value from address 0 that we have? And it turns out no, because we have another element that is not used, and that is in the same set. So this element, right here, it currently has valid bit of 0, which means it's not used. So we can put our value that we brought from main memory in here without replacing the word from address 0 that we previously cached. Okay, so obviously, so far we have 2 misses. All right, so it's still not much better, but we see that the potential is here, right? We were able to not replace word from address 0. So when we perform our next instruction, load 0, oh, finally, we expect some good stuff to happen here. We're gonna have a hit, right? Because yes, a miss on the second element of their set, but a hit on the first element. So finally, we are able to improve on our miss rate. It's now 6 to 7, because we have 1 hit out of 3, so 2 misses out of 3, but it is better. Then 6, let's see what happens with 6, load from address 6. We are checking which set. See how in the case of two-way set associative cache, our index is just 1 bit. All right, because we have 2 entries per. We have 2 sets, so we only need 1 bit to decide the set. But then, of course, we need more bits for the tag, because now we have more. We have to consider all those 4 bits when we are checking the first entry and the second entry, whether it's their data from the memory address that we want. So now that we have mapping to the same set, of course, it's going to be a miss. But then, of course, the question becomes, well, where do we put this data from memory 6? And now we have to do the replacement. Okay, so that's where this replacement policy kicks in. It tells us which of the two options, this one or this one, we are going to kick out of the cache and replace with data from memory address 6. All right, and so we had first in, first out. So that means that whichever entry was entered first is gonna leave their cache or be replaced also first. So we replace what this entry, which was previously block 6, data from memory at address 0, right? So we replace it with data from memory at address 6, and we proceed. So now we have just one hit out of 4. But next time when we read 8, we didn't replace 8, and that's why it's gonna be still in their cache, and we are going to have a hit. And all in all, 5 instructions, and we had just 3 misses. So 60% miss rate, much better than 100% miss rate that we had before. And finally, fully associative cache. All right, let's play with that one, and it's going to be the same instructions: 432 and nothing else. 432 and 0, nothing else to configure, and then we start with 0, and we have this. See how there's just one set with 4 entries, and any value can go anywhere. So let's submit the first instruction, and of course it's going to be a miss, and we bring it in and put it in some entry in our set, in some in some part within our set, in any entry. And then next instruction is going to be 8. So again, it's going to be a miss, and we brought that in and put it in the second element of our set. Then next instruction is load 0. We expect that it's going to be a hit because we have this value in the cache. And let's verify that it is indeed going to be the case. Yes, you see that we have a hit. Next is going to be load 6. 6 is not going to be in the cache. So it's going to be a miss, but we brought word from data from memory address 6 and placed it in our cache without replacing any of the blocks, any of the elements that are already in our cache. Right? So when we read 8, when we do load 8, it's going to be a hit again, right? Because block 8 is here. But in contrast to the previous example, if we just do another instruction, load 8, load 0, right? We see that, oh, now load 0 is going to be a hit, right? Because we still have it cached. We didn't replace anything. So you see how this flexibility in that gives us more associative caches of where to put an element if we need to bring it into the cache. It allows us to have fewer replacements, and it allows us to better utilize the cache, and therefore because more the cache is used more fully, if I may say that, then it means that we are going to have fewer misses. There's two ways set associative means has two cache, has same index. It means that the index now corresponds not to an entry, but to a set that contains 2 entries. and there is no indexing within the set. Remember, a set is a data structure that is not ordered. And that's why when we know which set a particular address maps to, then we have to check all entries in the set, because we cannot assume that the set is filled in any particular order. Okay, there is no ordering in the set. Is that making sense? All right, so that was this example. Okay, we just made it interactive, and yeah, so this is a confirmation of our hopes that yes, indeed, associativity decreases miss rates, and we have seen it even in this simple example that we just went through. However, the associativity a better, a high associativity decreases miss rates with diminishing returns, which means that, if we go from one-way to two-way, their miss rate is lower significantly. If we go from two-way to three to four-way, it's lower. It's still, noticeable, but it's, not as big of a difference. When we go from four-way to eight-way, then this increase is even smaller. What would be the optimal cost performance associativity? It's an incredibly difficult question, because you need to factor in the cost, which we are not talking about here, to avoid any conversations about the physical level, like their silicon die and their technology that is used to produce transistors, because then it determines how many transistors you're going to have, and it's getting more complicated. It's a valid question, but I wouldn't be able to answer it without bringing in a lot of additional detail that I don't think we have time for, unfortunately. All right, so of course now we can imagine their chart for their Set Associative Cache organization. So it's gonna look like this, and so this is the memory address. So from your load and store instructions, right? So this is our cache right here. All right. So we need as many comparators as which parameter of their associative cache. Or put it differently, when we say way associative, so what should I put here? Which number should I put here? 4, exactly. Yep, so it's a 4-way associative cache, because we see that, well, there are actually 4 entries per set, right? So you can think of, so this is the set number, all right? So this is like set number 1. So this is one set. Note that each entry would have its own tag, its own valid, and of course its own data, right? But it's imperative that each element would have its own tag and valid, because you remember we start with all valid bits being 0, right? They are all unused, and then when we use some of their elements within that set, we can use them in any order. So we can, let's say, start using this, right, and then put something in their tag bit, and then put something in the data field. So we definitely need a valid bit to go with every element, not one V bit per set, one per entry. So we're going to have 4 valid bits here in this example per set. And also, this should really, really, really confuse you. All right, can someone tell me why this part is confusing? What is confusing about this part? Or in other words, if I didn't say anything else, I would hope one of you would, would tell me, hey, Dr. Kurzman, there's something fishy going on. You ought to explain what is going on here. That doesn't look right, or at least it doesn't look familiar. So well, it's not OP. Well, depending on what you mean by OP. So it's a 4 to 1 multiplexer. So how many selector bits does it require? 2. Why do we have 4? Well, the answer is actually that a typical multiplexer that we have been discussing so far, it has internally a decoder, right? So 2 to 4 decoder, right? So you have those selector bits, and then internally it translates it to 4 outputs, only one of which is going to be 1, all others are going to be 0, and then it basically determines the rest of the schematic. In some cases, as you can see in this example, it is convenient for us. We already have these 4 signals that are decoded. So there are multiplexers that take in not the encoded value, right? Encoded means that we treat selector basically as as encoded number, right? So it's like 1, 0, 1, 2, 3. It's encoded. It's a number. But there are cases when we might prefer the multiplexer to take their decoded, the decoded selector. So 4 bits of a selector signals, only one of which is going to be 1, and the remaining 3 are guaranteed to be 0. And of course, which one is 1 would vary, but it's always going to be one selector bit. If we are talking about decoded selector bits, is going to be 1. Okay, so why is it? Why does it work here? Why there is a guarantee that only one bit is going to be 1? Well, because we assume nobody would want to store the same data from the same memory address in more than one entry in our set. So if we have a particular value of a tag here, 0, 1, 0, 1, I don't know, doesn't matter which, right, and valid bit of 1, there will be no other entry anywhere in this cache with the same tag bit, all right? And I mean, not anywhere in the cache, but anywhere in this set. So this is not possible because it would mean that we stored the value from the same memory address in several entries of the cache. Why would you want to do this? No, you don't. Okay, if the value is already in the cache, you just use it from the cache. You don't store it in another entry in the cache. That is what guarantees that only one of those comparators, well, one of those units, which is a comparator and an AND gate, is going to, at most one, is going to produce true, right? So we might have 1, 0, 0, 0. We might have all zeros. We might have ones in one, here, but not here. So we only going to have at most one out of these 4 outputs. All right, yeah. So make sure you know where things are coming from. So 32 bits are those. That's our data, right? So that's obviously our data is a word, so it has to be 32. So our tag is 22. That's why from tag entry we are getting 22. So obviously the comparator compares their same number of bits, so it's 22 here and it's 22 here. So then 2 bits here is our traditional byte offset, because unlike that simulator here for the textbook, we in most cases assume that the memory is byte addressed. So this address is the address of a byte, not the address of a word. So if we are thinking about words, we should allocate these 2 bits as the offset of the byte within the word. And then why do we have 8 here? Well, because we have 256 sets. And to address each set, we need 8 bits. That leaves 22 bits for the tag. All right, so replacement policy, which we briefly spoke about for direct map, obviously we have no choice, right? If we have to replace, there's only one element because each set contains one element, and that's the element that we replace, no choice. For set associative, we prefer first to use non-valid entries. So, if we need to bring a new value in, and we first look for an entry with a valid bit of 0 in the set that maps to this address. If there is one, that's quite natural. Otherwise, if all if all entries in the set are full, and which means they have valid bit of 1, we have to kick out one of the entries, right? We have to choose among the entries in the set that we have and replace one of them. And exactly which one to select to be replaced is the replacement policy. So I already mentioned least recently used and random, and there's a few others. But obviously least recently used is kind of fancy. Well, random is very, very unsophisticated, not discussing how you actually generate a random number or random anything in hardware, but conceptually it's very simple. Basically, just select any, okay, and that is easy. It doesn't require a lot to implement. If we think about least recently used, LRU is a lot more sophisticated because you have to keep track of which entry was used when. So there are different approaches to this. One, simple is just to, keep track and have a table is that is modified for each entry of their set when it was accessed. Okay, so and then when we need to replace something, select the entry that was not used the longest time. And it is fairly simple for two-way set associative caches. It's getting pretty bad, but still okay-ish for a four-way. And for anything beyond that, especially for fully associative caches, it is pretty much prohibitively expensive, prohibitively complicated. So you would rarely see this LRU replacement policy for fully associative caches unless they are really small. All right. So that, but we don't stop here. So far we have been in the paradigm of just two memory levels, cache and main memory, and of course the processor, which is not memory, right? But the processor talks to cache, cache talks to main memory. We can actually have more levels of cache because, for example, we might be very limited in the amount of cache that we can place on the same chip as the processor. So that would be our first level cache, and it would be very, very small because their price of each square millimeter on the surface of their chip where the processor resides is enormous. So we might still want to use fast memory SRAM, but it would be a physically different chip, and it will be level 2, level 3 caches. So we can have additional levels of cache. Each subsequent level will be larger, which means it would be cheaper so that we can afford larger amount of it, but it would be slower because it will be further away from the processor. It would still be a lot faster than our main memory, our DRAM. And we would still follow the organization where levels of memory can only talk to each other, to its immediate neighbor, but not across the neighbors, right? So main memory we would have our primary cache attached to CPU, and then level 2, which would satisfy the misses from the primary cache, and then a main memory attached to L2 cache, and main memory would be satisfying misses from L2 cache. And most current high-end systems also have level 3 cache as well. So here's an example that shows why multi-level caches actually improve their performance. So imagine we are given our CPI of 1, clock rate is 4 gigahertz, And miss rate for instruction memory is 2%. Main memory access time is 100 nanoseconds. So if we just have the primary cache, meaning the processor, primary cache, and main memory, no L2, no L3, then our miss penalty is 100 nanoseconds divided by the period of our clock cycle, right? So this is 1 over 4 gigahertz. Gigahertz. All right, so it is going to be 4 cycles. That's our miss penalty. You see, it is huge. CPI is 1, and miss penalty is 400 cycles. So if we compute the effective CPI, right, it's going to be 1, which is our CPI from here, and then 2%. Luckily, we only have relatively few misses, right? So 2 misses per 100 instructions. But each miss is 400 cycles. And if we compute the effective CPI, it's 9. So it's like, on average, our instructions, each instruction, no matter which one, takes 9 clock cycles. Whereas if we didn't have misses, we would have 1 clock per instruction. So it's like 9 times slower on, if we have to run, let's say, 100 instructions. Each instruction out of those 100 will run at 9 CPI. So the entire program would take 900 cycles instead of 100 cycles, which would be the case if we didn't have any misses. Just because out of the 100 instructions, all right, so we can do a very simple computation. 100 instructions, so we have 2 instructions that cause misses. Okay, so 200 instructions themselves are 100 cycles. But then 2 misses each brings 400 penalty. All right, so it's 400 times 2. So we have to do plus 2 times 400. So it's going to be 900 cycles that it takes to execute our program of 100 instructions. Whereas if we didn't have this component, it would be just 100 cycles, right? A difference, a factor of 9, almost an order of magnitude. That's huge. So what happens when we add L2 cache? And now we have our processor, our primary cache, our L2 cache, L2 primary cache. This is CPU, and this is our main memory, and I just write DRAM to indicate that it's a different memory technology, right? So with this, typical example values for L2 cache, access time 5 nanoseconds. If we compare, yes, it's not nearly as fast as CPU, but it's 20 times less than our DRAM, okay? And then we have a global miss rate to main memory of 0.5%. So this is, why does it say global miss rate to main memory? Well, that's because this is when the address that we are trying to find is not in, the primary cache is not in the L2 cache, and we need to bring it in from the main memory. So primary miss with L2 hit is going to be just incurring a penalty of 20 cycles. What is this? It's when the address that we are trying to access, it's not in the primary cache, but it is in the L2 cache. So, we are lucky we don't have to go to the main memory because the value was cached in L2. So the penalty is just 5 nanoseconds divided by 0.25 nanoseconds, so just 20 cycles. So compare this with 400 cycles, right? So when we had to go to main memory, the penalty was 400 cycles. Here it's just 20 cycles. So primary miss with L2 miss, well, that's not so good because there's an extra penalty, 500. Why 500? Well, because we still had to go through all levels. So there was 100 penalty here, and then a 400 penalty for for here, right? So it's this penalty right here, 400 cycles additional. So all in all, it's 500 cycles. So our CPI, if we compute it, it's 1, which is our ideal CPI, and 0.2%. It's 0.02, so it's 2%. It's this value here, right? But now instead of 100 cycles penalty, we only pay 200 cycles penalty if the miss to primary cache is satisfied with an L2 cache, and if it is not, then we pay this penalty of 0.05, which is the miss rate to main memory. So it is 0.5%, but the penalty is still 400. But we were able, by introducing L2 cache, we were able to bring this miss rate to main memory from originally 2% when we only had 2 levels of memory to 0.5% when we have 3 levels of memory. So all in all, it's CPI of 3.4, and if we compute it, it's almost 3 times better than we had. We used to have CPI of 9, now we have CPI of 3.4. By introducing an additional level of memory, we were able to improve the performance of our instructions by 2.6 times. So that's pretty significant, and that's why multi-level caches are used pretty much everywhere. So primary cache focuses on the minimal hit time, and then L2 cache focuses on having the absolutely minimal miss rate, so that we can avoid main memory access, as much as we can. And hit time overall is not as important for L2 cache as it is for primary cache. So the result is that our L1, our primary cache, is usually much smaller than a single cache, but L1 block size is smaller than L2 block size. And interactions with advanced CPUs. So I'm gonna skip this slide. So it's getting complicated. We largely can only do simulation to model what will be going on with those superscalar CPUs. You can't really compute it with a formula. All right, and here is your next pop quiz, number 3. All right, so interactions with software. We need to make a note that the performance of cache significantly depends on the algorithms, on the program that you're running, on which, how algorithm works, and how efficient compiler is in optimizing memory accesses. And this is just one example where you look at the same algorithm, comparison of 2 algorithms, radix sort and quicksort. Nothing really interesting happens with quicksort, all right, and the different plots show different values: instructions per item, the first one, clock cycles per item, and cache misses per item. So if you just look at their instructions per item, right, so this is the size along the x-axis, the size of the array that we are sorting. And obviously, as we increase the size, the number of instructions per item to be sorted, it drops for radix sort, right? You see that it is slowly dropping. For quicksort, it increases slightly, which is to be expected. When we translate this to clock cycles per item, then we see something really, really weird with the radix sort, right? Quicksort is not susceptible to this, but with radix sort, we see that there is clearly this turning point that our instructions per item keeps decreasing, which we see from the first plot, but we are actually spending more time in those instructions, right, on fewer instructions than before. We have fewer instructions per item, but we are spending more clock cycles, more time per item. Not by much, but still, it's not. Is it non-decreasing, but it's actually non-decreasing. It's actually increasing, strictly increasing. And if you and the answer is, well, we have to look at cache misses, and you see, oh, right here, right, we have a pretty sharp increase in cache misses after we so once we go past 64K items to sort, once our array is greater than 64K. So and this is exactly the explanation, right? If we have a sufficiently large enough array to be sorted, then when it no longer fits in completely in the cache, certain algorithms will be very inefficient because we will be replacing items in cache over and over again. So we're going to have a lot of cache misses when the entire array does not fit in the cache. And as you can see, some algorithms are more susceptible to this than others. So it's also a function of the algorithm, like radix sort. Their canonical implementation of radix sort is obviously susceptible. All right, so and we can help their the compiler and the system by writing our code so that it is optimized and using blocking technique. Basically, blocking means that we access values that are blocked together so that we can hope that all elements within the block that we are accessing, it fits in cache completely. So not the whole data set fits in the cache, but the entire block. So it is sufficient just for the block to fit in the cache. And of course, the entire data set consists of multiple blocks. So here's an example, and so I won't go over it in very much detail, but consider our double general matrix multiplication example that we have seen before. This is the canonical, like straightforward implementation. And if we look at the access patterns, we see that it is very irregular, that we are performing accesses earlier, and then we move forward just to come back to accessing the same elements that we used before, but that have been replaced because we go through the entire matrix in each of the loops, right? So and that causes a lot of cache misses. Whereas if we go with a blocked access, so let's say we define a block size to be 32 elements, and then we access only elements within the block, right? So you see here's the block size here and here. And of course, then we need to, go through all the blocks. So we have to have loops that increment their block size here, okay? So that this Sj grows in increments of the block size, 32 in this example. But then we have a doBlock method that computes the values within the block, right? So that's why it increments by 1, but it only goes to the index plus the block size. Then our access pattern is going to be much better. So because we are confined within one relatively small block, let's say 3 by 3 instead of this whole 6 by 6, then of course the locality of our accesses will be much better, and you can see it with their access times. This plot here, unoptimized, their lower the worse, right? The higher the better. We see that as we grow the size of their matrix, right, from 32 by 32 is not going to be any different because it will fit, the entire matrix fits in the cache. But for 960 by 960, the entire thing doesn't fit in the cache. And you see that the performance in an optimized canonical implementation of DGEMM drops significantly, right? So this is GFlops, giga flops. So the higher the better, and we see that it drops. With the blocked access, we still enjoy the locality. Our block is 32 by 32, so our performance practically does not drop as we increase the size of the matrix. All right. We are here. It's 1:49. So yeah, let's then stop here. You are lucky. Virtual memory is not going to be on this upcoming exam. Yeah. But we will still talk about it. So I would rather finish with virtual memory on Friday and then, leave chapter 6 for you to study on your own, then do the opposite, right? So virtual memory, you're gonna enjoy a lot of this topic when you take operating systems, right? So you're gonna love virtual memory. You're gonna spend a lot of time on talking about virtual memory in operating systems. So, I just wanted to give you a heads up and show a little bit of under the hood how virtual memory works at the hardware level, whereas in operating systems, you will be focusing on the view of virtual memory from their, slightly higher software level of their operating system. In case we got to it. Why was it in the lab review, Paul? Yeah, so, you know, the review is not only for the exam, right? It's just for all the topics that we studied. And obviously, since we didn't talk about virtual memory, then we, you know, we don't expect you to ask questions tomorrow during their lab review time. Okay, so we're going to discuss it on Friday. Is page memory and TLB not going to be on the exam? Yes, because well, it's not page memory. It's paging and TLB. That's all part of the virtual memory topic. Wait, how many questions are on this exam? I don't know. I haven't written the exam yet. Can compiler do any of the blocking? Not possible? Yes, it can. All right. Yeah, I believe this is it. If I missed any questions, then please feel free to remind me. I can stay a few more minutes online. But for the rest of you, for all of you, enjoy the rest of your day. Good luck on the exam tomorrow. Please come to the Q&A session tonight at 8 o'clock, 8 p.m. on WebEx. And of course, please attend your lab review exam preparation session tomorrow during your lab time. Thank you very much, folks. Have a good one. All right, and now let me see if I missed any questions. For the project, instead of shifting by 2 bits, do we just sign extend by 2? Well, those are not the same things, right? So shifting by 2 is like multiplication or division, depending on which side you shift. And sign extension is just a way to preserve the value of the number if it's in 2's complement notation and you need to represent it with more bits than you currently have. So those are not the same thing. All right, and slide 56. Slide 56.